Please come on. Okay, thank you very much for joining my class. Uh, okay, let's start our today's lecture. Please sit down. So, today is our very first class of applied electromagnetics. So uh, I I assume you are all part-time students, right? Right? All of you. Okay, so uh, we are going to start our SCHS 3314, which is applied electromagnetics for of electrical engineering. This is one of the fundamental and core subject of EE, right? Uh, Many of the EE subjects that you will face in your upcoming semesters would actually require this subject's knowledge and fundamental skills, right? So this is going to be a fundamental or basic or foundation course that will help you in other subjects as well. Or if you are going to pursue a higher degree or higher courses, trainings, this would be a must subject for your further, career improvements. Okay. So I am Dr. Sheheryar Khan. Uh, I'm the subject leader and also the lecturer for this course. So I'm going to teach three class sections, right? One on Monday, one on Wednesday, and one on Saturday. Okay. Usually we follow the strict policy that the students they should join their respective class sections. So I understand you are part-time students. So in case you have some emergency or you miss some of the lectures, you can still follow the recordings. Or if you want to join face-to-face lesson, you can send me an email and I can help you to arrange another alternate class sessions, right? So usually we will go parallel with other sections as well. So I am here at CPC for last more than 3 years, and this is the subject that I am teaching on regular basis along with other subjects of EE. So if you want to enjoy this course, so I would require your full attention. And meanwhile, if you want to chat with your friends, I can give you some time and then you can enjoy. Okay. So when I'm speaking, so I would require you to concentrate. And I really enjoy questions or you have some interesting information to share. You are most welcome to interrupt me at any time. Okay. So during the class lesson, we usually focus on our subject and we actually mind our business. That's the story. So uh, as far as my teaching career is concerned, here's a short introduction. You can also see my profile on the CPC page. You can see the research interests and other activities. I'm teaching here other subjects, including the electric circuit analysis. That includes the DC circuits, DC AC circuits, devices, digital circuits, and the other engineering subjects that include society and engineer. So my preference for this subject is actually to introduce the strong skills, foundations, mathematics, principles, and laws that will help you to understand the common engineering applications that includes electromagnets, that include relays, and that also include complex electrical systems that we are going to discuss in our upcoming lectures. So here's a quick uh, introduction and also the uh, communication, how you can communicate. So You can send me message usually on the Blackboard, or you can email me, or if you have some serious concerns, uh, I would also love to share my WhatsApp. Okay. You can send me WhatsApp, or you can call me if you have some, emergency issue or to discuss with me. So uh, I will try to upload the lecture notes and the other helping material on the Blackboard portal for you to consider, most probably at least one day ahead. Okay. So you can follow those materials and then we can discuss in our lectures. So here are some of the objectives that you will find. I have also uploaded the teaching plan and the assessment guide for you. You will see all those objectives very clearly on those documents. Uh, so this subjects aim to comprehend the electromagnetism, physical quantities, electromagnetism, basic relationships. Actually, we will study the very basic foundations of electromagnetism. That means first we will study the electricity alone, then we will study magnetism alone, and then we will study the impact of both quantities, right? So you will see that will include the charge objects, that include capacitors, that include inductors, and their relative devices, their sensors. And then we will conclude at the uh, AC analysis, which is actually the electromagnetic induction principles, right? So far, all those materials, they look quite distributed, right? But we will shortly put them in a real picture for you to study. Before we discuss the course outlines, let's look at the assessment and weighting. We have 40% continuous assessment, 60% is the examination. For the CA part, uh, we have one assignment. That's a written assignment. So usually that includes some numerical based problems. Attention, please. So assignment one includes some practical problems that are similar to what we will solve in our tutorials. Okay. So we will study some principle, we will derive some formulas, we will understand some principles, and then I will give you a problem, and then you need to just apply the formula. You can solve the problem, or you can just give out your answer. Okay. So that includes the assignment one. Assignment two is the laboratory experiments. We will also have two laboratory sessions. So the different student will have different groups, right? So you can check your own laboratory group on your timetable, okay? Then we have a class test. We can negotiate the exact time of the class test. Usually I prefer 6th to 7th class lecture, okay? So we can decide which week suits our schedule, okay? And then we have a 60% examination. For the examination, uh, the the overall exam is designed in such a way that it starts with the very basic questions, right? So the first question, uh, if you are attending the lectures regularly and you are taking part in the class discussions, or at least you are looking at what we are doing, I'm confident you can pass the first question very easily. Okay. Second question, of course, requires a certain amount of knowledge. Third question, more. Fourth question, more, right? So that's how the exam goes up. But for the exam, I can share with you the past 3 years question papers along with their solutions. So In my previous practices, what we do actually, please, is we reserve certain time at the end of the course, and I help you students to solve the past papers, right? So I show you the questions and then also discuss the questions and then tell you that what kind of trick is involved in the question, and then we give you the solution, right? So that will give you a, the a practical experience how to, tackle with the questions. So for the full-time and the part-time students, I have observed uh, a very interesting pattern. Those students who are very attentive and responsive, and also do not miss the lectures, right? They usually get higher grades, right? So majority of the students can easily pass the exam. So this subject is something like that. Teacher can prepare a very challenging question, or teacher can prepare a very easy question. So it depends. So it's a very vast subject. However, in our subject, because we are looking for the applied concept of the electromagnetism, right? So we are not going towards the deep theoretical knowledge, although it's a requirement. It's required, it's necessary, right? But we will actually focus on studying and understanding the theoretical concept and the laws and formulas. And then what we ask is how to apply that knowledge and skill into a real world problem, okay? So in my observation, uh, if you are serious, at least all the class students can get passing marks, right? If you're serious, right? At least you are taking actively participating in the class lectures, asking questions, or at least solving the tutorials, right? Or going through the regular class assignments like CA and the midterms, right? Then you can easily go through the exam. That may not be an issue for you. Okay, so for our teaching plan, this is a approximate teaching plan, right? So we may have several topics that are being overlapped, right? So depending upon the class communication, we usually have a certain amount of relaxation between those topics. So in today's lecture, I'll give you some introduction. We will have a general discussion, some video demonstrations, and a very simple explanation of the basic definitions. Lecture 2 and 3, you would see we would have a discussion on some mathematical preliminaries, right? Uh, because for the uh, last experiences, I have seen part-time students, because they have some of the students have a certain gap between their last degree or last diploma. So they are not quite well prepared in terms of the mathematical formulations, such as some derivations, some mathematical operators. Right? Therefore, we spend quite a handsome amount of time on deriving some mathematical preliminaries. Now, you may ask that why we need this, why we can't directly jump on the problems to solve. Actually, for this subject, we will see later that uh, electric and magnetic field, as the name suggests, they are vector quantities, right? So they have a certain direction, right? So when we say direction, then we talk about the 3D space, right? So therefore, we need to understand the directions, the 3D space. Therefore, we will look at the vector spaces, right? How the coordinate system, just like the rectangular coordinate system, right? X, Y, Z components. So we have a certain components that we need to discuss so that we can understand the amount of fluxes and the vectors within certain materials, right? For example, you can consider an cable, right, that has some current passing through, right? Some of the students can easily solve the problem. We can apply the KVL, KCL, just like Ohm's law to solve it, right? But that's very good if you have some understanding of the DC knowledge, DC information, like we have a third of DC value of the voltage and current resistance, and you can solve it. However, there's an AC source, then you can use the phasor analysis, right? You may have studied or may have heard about the polyphase circuits, right? So you have three-phase circuits, you have some, you solve them, right? That's good if you want to find out some value up, or if you want to calculate the power consumption of the load of the source, that's very good, right? But we are not talking about some ahead of it, about the amount of electric field or magnetic field produced by that particular source, or we may be interested in finding the flux or maybe the force in case of a motor, right? Therefore, we need to understand how the flux is generated, what's the direction, and how it's distributed on the surface of the conductor. So if you look closely to the conductor, the wire looks like a cylindrical shape, correct? So it's less like a cylinder, it's round, right? So we need to understand how the vectors perform in a cylindrical shape. That's why we need to understand some cylindrical coordinate systems, right? So, so you might be thinking that it could be very challenging. No, it's not challenging, because what we will do is, for all the mathematics that we study is just for understanding. So we do not require you to memorize it, right? For those formulas and the derivations that we study and I demonstrate to you, in exam, we provide you the tables for all those formulas. So you don't need to memorize it. It's not a memorization, right? So you just need to understand that what actually it's saying and how should I use it. But I'll still explain to you. I'll look at the derivation and I will help you to demonstrate where these formulas come from, okay? So we will look at some mathematical operators. Apart from the vector analysis, we have some topics related to the coordinate systems, and then we have some topics related to the gradient operators, right? And then we have our main business here. We have static fields. Uh, so the static fields represent static, that means that does not change with time. Okay, that's what we study. So for the static field, we look at the electric fields. That means the charges, only charges. So one of the example is the capacitor, right? So you have a simple charge deposit on the plate, that's static, okay? Then we look at the static field in terms of magnetism, so how the DC current can produce static magnetic field. That's a simple electromagnet. So you pass a current to the coil and it produces an electromagnet, that's it, right? So we look at the whole story about this thing. Now, after this story finishes, we look at the time varying fields. That's going to be very, very interesting. So the time varying means that something that goes up and down, what we call sinusoidal, or in your language, we call it AC waveform, alternating current, right? So we have daily applications of AC outlets, right? In time varying fields, we see that how we can use this to have some interesting application. One of them is I would say the mother of all foundations. That's the generation of electricity. So how the electricity is produced is actually due to this thing, right? So that's what we call the electromagnetic induction. It's how the electricity is induced, right? So you see the generator, right? So you have a generator, a simple diesel engine or a petrol engine rotates certain coil, and then you have an electricity produced, right? So that's what we call the induction, how it's induced, right? So we look at the time varying fields. And of course, we can have an opposite effect. So you supply an AC wave and then you have a motion that we call the AC motor or induction motor, right? And then within those fields, we have certain other topics to discover, such as material media. What kind of materials are good for producing electric fields? and how they behave. We will look at the materials such as the ceramics. We look at the if you haven't traveled on the MTR, you would see some round shaped circles hanging, right? That are the high voltage insulators. Right? That's are the materials. We will also look at some magnetic materials. So you'd see when you have a transformer, you would see some iron core, and then there's some coil wrap on it, right? That's a magnetic material. So we look at those materials that helps in the presence of electricity as alone, materials that helps us in the presence of a magnetic field alone, right? So we will look at all those things, and then we will combine those concepts into a group of equations called the Maxwell equations. Actually, those fundamental laws in electromagnetism, they are uniquely represented into a Maxwell equations. Actually, we will start deriving the Maxwell equation right from the next lecture, but uh, in our daily usage, we usually use the names according to the laws, such as the Faraday's law of electromagnetic induction. Right? We use uh, the uh, current law. We use the Ohm's law, right? So all these equations, they can be summed up into the Maxwell equations, right? So that's the whole story. And meanwhile, we will look at certain applications that are actually helping us, right? Based on these all these concepts. So at the end, we will spare some time for our exam review. And for the class test, we will also arrange a certain time for you to revise the previous material, so that can help you to prepare for the midterm test. Okay, so I can give you a mock test before the midterm, so you can see how to solve it, and then after one day I can give you the solution for this, right? So don't worry about the class test and the exam, because I will give you the samples for you to prepare. Okay, so that's the whole business that we will discuss. Uh, this one is the book that we were going to follow during our lectures. All the lecture notes and the slides, they are prepared or taken from the first reference. But you will also see similar type of examples, solutions, numericals at the second reference. Okay. Okay. In the next few slides, uh, I have collected some information for you about the subject. That's a general discussion. So in this course, the main problem lies in the complexity of the devices. If you have studied the linear circuits or the electric circuits 1 or electric circuit 2 or circuit theory, you have seen that we have a very simplified circuit. We have a DC source, we have AC source. Sometimes we have a models of different sources, uh, and we do not discuss what type of source it is. And we have simply connection between several elements. We have a resistors and we just connect them. And then when we calculate the power dissipation, we just assume everything is perfect, right? The source does not change with time. The conductors behave ideally. There's no drop in the conductors. The connections are perfect. The devices does not change with the other conditions. But in actual practice, things are quite different, especially when you move to a high frequency, or the when you change the energy or the intensity of your signals. For example, in computers, we have a hard drives that use magnetic tapes to store the data. We have communication between devices that is based on the high frequency. We have cellular communication. We have a communication between two links that actually either a optical fiber or maybe a high frequency connection. So these high frequencies or even high power electronics that the voltage or the current rating are higher than the normal usage. So all these systems, when we have a transients, when we have a inductors, when we have a capacitors, when we have a fast switching, right? So then the circuit does not respond ideally that we are actually thinking, right? In order to properly model those circuits and solve these parameters, we need to understand apart from the VIR and the power, we need to understand external parameters. So what are those external parameters? For example, for capacitor, you must know that what's the material actually, right? Whether it's air, whether it's mica, whether it's glass, whether it's water, right? So this will actually determine the value of capacitors, right? Okay, for when you know the capacitance, then you can find out the energy stored in the capacitor, right? So the V and I are not enough. For the electromagnetic circuits, apart from the V and I and R, you must know the amount of flux required, right? You must know the inductance, right? You must know the coil inductance. Then you can find out the energy required, and then you can find out how much charge, how much energy it will retain in terms of magnetic field, and then how much power it can supply, right? So that's the reason why we need to understand those concepts, especially when you are dealing with the electric and magnetic fields. We must go through some, the basic principles behind them, right? Therefore, you can consider that the electric circuit theory is actually the derived form of the electromagnetism, right? So when you summarize or made some assumptions, then you can use electric circuit theory. But actually, you have to consider those practical concerns regarding those electromagnetic circuits. So as you can see, I mentioned is the basis for many devices. So when we say machinery, that actually means motors and generators, right? So when you have a electricity and then how the voltages can produce or induce currents, right? And then how they can produce magnetic field, and then how you can get the motor working, right? So for when we say antennas, then we have a the high frequency components, right? For our subject, we will limit ourselves towards the EM equations, right? So we will not proceed further. However, in electrical engineering, if you proceed towards the communication side, then you study the antennas and microwave communication as a separate subject, right? For this subject is actually the basis. And then, or if you proceed towards the power engineering, then you go towards the power subjects, right? So there are two domains. Right, from this subject, either you can go towards the power transmission, distribution, utilization, or you can go towards the antenna, microwave communication, cellular communication, satellite communication, right? So all those are based on these electromagnetic fundamental principles. So again, we are explaining here. Uh, I'm sorry for this delay. My device is maybe is lagging behind this internet connection. So let's see this figure out. So as devices get smaller and smaller, what I've explained, we have a written form here. The frequencies, they increases, circuit theory is less applicable, right? Transmission line, guide wave theory, and there are practical applications in different fields such as fiber optics, microwave, antenna, optical communication, electromagnetic interference, compatibility, biology, medicine, biomedical imaging. So before going further, may I ask, because these are the devices that actually we currently use. So optical fiber optics, we know that the current broadband services, right? They provide a extremely high data rate, right? Because the due to the conversion of the the signals into the optics. Microwave communication system, we know the cellular communication from the base stations, antenna wave propagation, optical computing. We have furthermore. But how about these terms? Biomedical imaging. Heat from what kind of heat? Heat from the body. Okay. Any other concern? I mean, what's the applied electromagnetics had to do with the imaging, radiation, black body radiation? Yes. Any device that we use in our daily life. X-ray is one. No, yes, you're correct. Remote is correct, but we are just discussing about the biomedical imaging. X-ray is one of them. Perfect. Any other? Any other? Yes. So if you would study the MRI, that requires a separate subject, not a class. And MRI is a complete example of pure electrical engineering. There is no, artificial sort of acquisition inside it, right? So as we can see in our smartphones, we have a camera, right? So that's some sort of artificial processing, right? However, if you go towards the mechanical camera, right, the optical device, that's pure physics. Pure physics. You have a certain aperture that captures the light, and then you have a film, and then the image projects on it. That's a pure physics. Similarly, your MRI machine is pure physics and a pure gem of electrical engineering. I'll show you some video later, but it's just because of the electromagnetism. And it's not just a device, actually. It's actually a human body that has a built-in characteristic of electromagnetism. We will study in our next video. Because our body is 60 to 70% water molecules, right? H2O. And the hydrogen had a specific electromagnetic field. And all the atoms, they are spinning, right? So they have electromagnetic field, right? That means that if now you have some powerful magnet, right? So the main magnet can interact with the magnetic field of all the atoms in the body, and they can align them, right? They can force them to move, right? Let's say if the hydrogen atom is moving like this, right? Randomly, somebody's moving like this, somebody's moving like this. So they are present in whole body. Let's say they are present in the eyes, they are present in the brain, right? And let's say if you or somebody is unlucky to have some tumor or some unhealthy tissues, then the water composition is different in those tissues, right? And then you have a main magnet. Have you seen the MRI that has a circular magnet, right? That's a pure electromagnet, right? That's a pure electromagnet. Just wait. Yeah, that's a pure electromagnet. Extremely high current, right? Superconductor, cooled down to minus approximately 200, so that the current flows almost near to superconductors. Extremely high magnetic field, right? 2 Tesla, right? So this field is almost 100 times stronger than the ordinary magnet that we use in the twice, right? So let's say if I have my belt or some keys, I can place here and it can easily cache the keys in the room. So when a subject is laid down under the influence of this magnetic field, all the hydrogen molecules, they are aligned, right? They move like this. And then you have another coil that is placed around your brain or your knee or your chest, whatever the area of interest is, right? That has a special coil to induce another RF wave, right? That is perpendicular to the main field, right? That disturbs the distribution. And when you throw the signal on it, it disturbs the motion, and then you remove it. And then the molecules, they move back. Interestingly, when the molecules, they return back to their original position, they emit another RF radiation, and you have another coil, you collect the radiation. And imagine what? When you collect the radiation, you put a computer on it and do the Fourier transformation of all those frequencies, right? So the Fourier transformation, look at the intensity of all the frequencies, right? Which frequency has what amplitude, right? And then you can project into a 2D image. You keep taking 2D image and you have a 3D scan of your whole body organs. And interestingly, those abnormal tissues, maybe tumor or some unhealthy tissues where the composition is different, you can see a different contrast of them. And that's how you can actually project, sense, or create an image of the body inside it. Right? That's different from the imaging that we use in our daily life, right? So we use light to project an image, right? That's what is being done in our eyes. This is pure electromagnetism, right? So you can look at the some of the other application. So here is the ECG, right? Electrocardiogram. This is one-dimensional signal, right? So you place several nodes, sensors, and you actually measure or record the electric activity of the heart rhythm in terms of electric activity, right? So there's a special rhythm of the heart arteries, right? So you record those rhythm into form of a electrical activity. And then you have other EEG, right? That means also it measures the electric activity. But for this one, we measure the magnetic activity, right? So we have several other defense applications for this field, right? We have our communication, right? We have computer technologies, right? We have the Wi-Fi signals. We have the magnetic storage. We have the displays, right? We have communication technologies, right? So here is actually what we are trying to discuss now. Let me see if we are back on our, yes, coming back. Okay. So I'll show you the MRI video, but before we go there, let's look at the whole synopsis of our subject. So I hope you all have gone through this terminologies. So let's look at this. So electromagnetics is the study of charges, right? So we know that the charges, they move, right? Due to the potential, right? So they move from positive to negative, right? Conventional, right? And uh, sometimes the charges are at rest, right? When they are at rest, in terms of when the capacitor is charged, right? When you connect capacitor to the voltage, right? The charge deposits on the surface of the plates, right? And then there's no current, right? That means they are at rest now. How about the charges in motion? When a circuit is completed, let's say you connect a coil with the voltage supply, and the current flows in the coil, right? You have an inductor coil, and then you connect it to the battery, right? Now the charges, they are moving, right? They move. When they move, then we have a current, right? We will later see this current will produce magnetic field, correct? Now, so we have two conditions here. Charges at rest, that means you have a positive plate here, you have a negative plate here, right? And those plates will actually store the charge capacitor, right? So now there's no current. Current is zero, right? So we say it charges are at rest. When you complete a circuit, the current flows, you have a current flowing and charges are in motion. Now, there are two conditions further when you have a DC current and when you have a AC current. For DC, we use the term uh, static, right? Static means that the current does not change with respect to time. What's the example? The batteries, right? Charged batteries. You have a 12-volt battery, 3-volt battery, or even you have a solar plate, right? 6-volt, 10-volt, 9-volt. You see, the current does not change with time, even the voltage, right? Let's say if you have 5-volt battery, have you seen -5, 4, 3, 2, 1? No, it remains 5 if it's fully charged, right? If it's healthy, you buy a 5-volt battery, and then it remains 5-volt, right? And one of the example is your mobile charger, right? Our mobile charger, or even all the electronics that is being operated like mostly on DC, right? That's a static current. There's no variation. Later we see that this is actually the fundamental theory that gives us the blessing of electricity generation. This movement is a real blessing. We'll see later. So electrostatistics mean, that means that electro mean it's electricity, stat means static, right? Means charges are not moving. So we have this case, right? So we have no time variation. So it's a DC. No time variation mean actually DC current, direct current, right? And charges mean, that means there's only electricity. So the example is capacitor and its related applications. Charges on a capacitor, charges on a plate, right? Now look at magnetostatistics. That means that we have a charges that are in steady motion, right? Now we have a DC current. Here we have a only voltage. Current is zero because circuit is open, right? Stat means charges are not moving. If there's no motion, that means circuit is open. And then we have charges that are in motion. This case, inductor, right? Now that means that we have a DC current. So the example is you buy a battery from market, let's say 3-volt, you take a piece of uh, copper wire, make a solenoid, make it some turns and connect it. What happens? That coil will turn into a magnet, right? That will turn into a magnet. However, this magnetic field will be static, right? There will be a fixed magnetic field around that coil. So how to check it? So if you have a compass, you place the compass and then you can draw the magnetic field. Or if you have some iron dust, place the iron dust on it and then it will create a pattern, right? However, this pattern will remain as it is if you supply the DC, right? If you remove the DC current, the field goes away, right? That's what we call electromagnet. Please remember the stats mean DC, correct? So in the first case, we have a DC connected to some plates, no charges, motion. Second case, we have a DC, but we have a complete circuit. We have a complete, let's say like a solenoid or inductor. We have a current flowing through the circuit. We have a magnetic field, right? But the current is DC. Third case, what we called electrodynamics. Now the dynamics means AC, right? So AC is one example. Another example is you have some motion, right? Let's say I have a coil that has a DC inside it, but I'm rotating the coil, right? Again, a dynamic, right? If a coil has a magnetic field and I'm rotating it, that means I am changing the magnetic field. I'm asking the magnetic field to change. That's called the dynamics, motion, right? Where you see this kind of principle. Generator. Sorry? No. LC circuits are just tuned circuits. Yeah, these are for producing the resonant frequencies. So dynamics means we have some sort of real motion. So there are two types of motion you can produce. Either you have a DC and you mechanically move the coil, right? That means you put a diesel engine on the coil and ask the generator to the engine to rotate the coil, right? When you rotate the coil, it will induce voltage. That's what we call the generator turbine, right? Second thing is, rather than rotating the coil, you give a current such that the current is rotating. That's called the AC, right? So you have a coil and you give it a pulsating current, AC, right? So if you look at the AC, AC is like this, right? You know what does it mean? That's our AC outlet, right? 220 volts, right? RMS value. Root means square value. I will later explain. What does it mean? That means that we have a almost 50 hertz, right? That means that in 1 second, it has 50 cycles, right? So half of the 50th time is up and half of them is negative. So positive and negative actually means the direction. So in one half cycle, it goes this way, other cycle, it goes this way. So it increases like sinusoidally and then decreases, right? That's what we call the alternating current. So it changes the direction, right? So what does it mean? It means that the magnetic field it produces also changes, right? That's called the dynamics. We will have a separate chapter on it and I'll explain to you with demonstration what's the purpose of this one. So when we have this dynamics, then we have charges in time varying motion. Now something really interesting happens here. One thing I told you that the electrodynamics give us the electromagnetic induction, right? So if you have a generator, you can produce electricity, or if you have electricity, you can create a force and then you can, drive a motor, right? So that's one thing. But there's another important thing that it give rise to waves that propagate and carry energy and information. So this pulsation actually helps us to transmit a certain amount of wave into the air, right? That's what we call the wave propagation. Have you seen the wireless communication, right? Let's say you transmit something from here and you can receive something from there, right? That's the radio signals, right? Right. So we have wireless links, right? That travels with the speed of light. Actually, these are the light spectrum of light. So when you pulsate them with certain frequency, then I'll show you if you have a correct mechanism to receive it. You design an antenna and you receive a same wave with the special wavelength, right? Then you can receive that information. That's again the similar pattern of the wave. That's actually what we do in our daily lives. These are the carriers we transmit, we receive, transmit, receive, right? So we have analog communication, you see the frequency modulation, radio signals, right? So this is the another important theory. So uh, if you look at the course introduction, I show you mathematical preliminaries. So why it looks difficult? As I mentioned, we are not going to study the electromagnetic theory. This is not electromagnetic theory subject, although we will study and we will discuss it. Our subject is more applied. So we are not going to ask questions from theoretical point of view. We will ask you to apply something and then analyze something or answer something. Okay, so don't worry. So it's three-dimensional. As I mentioned, we have to think the vector fields into three-dimension. They are vectors, right? They are moving in one way, they are canceling another way, right? uh, they vary in space as well as time, right? This is for the wireless communication. And sometimes we also need mathematical operators in terms of the differential equations. I'll explain this also, don't worry. So we use some tricky mathematical operators to solve them, right? Therefore, it looks quite difficult, but actually it's very, very interesting. Okay? Uh, so maybe we have 1 hour past. So let's take a very quick break. And then I prepare a very good video for you. And then we can start our next section. Okay. Meanwhile, I'm here. If you have some questions, please ask. Maybe we take 5 minute break and you all can, enjoy restrooms. Oh, yes, sure, sure. Please, please. Thank you. Okay, so uh, class, please. So that was the simulations from the MRI. So let's look at our. So this is something we are actually doing here at CPC. This is our project uh, because we are not ac- doing the work on acquisition of MRI. We actually try to understand actually what's inside the MRI. So we try to segment those small tissues from the human knee MRI, and then we use the machine learning, specifically the deep learning based algorithms to do the segmentation, and then we can see how the human knee cartilage looks like, right? So the main idea is actually to to have the 3D representation of those tissues and see where there is a damage, right? So as you can see that it can actually give you the positions and the 3D view where the cartilages or the tissues they are being lost, right? So this technique or MRI is actually very very precise, right? So you can actually capture a very fine biochemical composition details of a human body, right? So as you can see, the whole process that being explained in the video has nothing to do with the light, right? So it's purely electromagnetism, right? So this is really interesting. We have plenty of other applications in the field, like ground penetrating radars, right, to sense the objects. We have imaging through the wall through the electromagnetic patterns. We have the radar based systems to detect the vehicle collision or nearby appearances, and we have several other material science applications, right? So you see, these are the high power insulators, right? For high power, high voltages, usually in the kilovolt range or even in the megavolt range, it's very difficult to the isolate the conducting material from the nearby objects, right? So we need to create or use specific type of ceramic, the insulators, right? So that can help us to get rid of the effect of electric and magnetic field, right? So otherwise they can produce leakage current, right, and easily get the short circuit, right? We will look at this, the voltage uh, when we use the materials. Okay, so another part uh, in the discussion, I showed you that when we have a uh, moving or dynamic electromagnetic radiations, then we have a not only we have induction, but we have actually the the traveling of waves. So does the so electromagnetic waves that we discussed, they are transverse wave made up of electric and magnetic. Transverse mean that when they travel, the electric part and the magnetic part or the components, they are actually 90-degree with each other, right? These waves travel at same speed. In vacuum, they travel 3 into 10 raised power 8, right? That's exactly the speed of light, right? Uh, Look at the electromagnetic spectrum. You would find several other demonstrations of this. You see, we can start from the left, we can start from the radio devices. So this on the top side, we have applications. On the bottom side, we have the wavelength. Now you see here we have a longer wavelength, right? But the frequency is low, cycles per second, right? And the energy is very low, right? So you see we have a radio wave communication. That means amplitude modulation and frequency wave modulation. You increase slighter, and then you have microwave for the heating objects. Then we have infrared waves, right? Then we have a visible spectrum. Do you know this visible spectrum where we can have the R, G, and B colors, right? Red, green, and blue, right? This is the visible spectrum. So actually, our eyes are band pass filters. So they can only look at a specific spectrum of the light. That's the visible spectrum. So for the infrared spectrum, it still exists, but we need infrared camera to see it, right? As long as you increase the frequency, the wavelength get more shorter, and interestingly, you have more penetration power, right? You see, we have ultraviolet, and then we have X-rays that can actually pass through the skin, right? But can produce shadow on the dense objects such as metal or the bones. But if you go more deeper, then you have a gamma rays. So these gamma rays can actually penetrate up to the cellular level, right? So you can use them to, for the radiographic therapeutic, the treatments such as in the cancer treatments. However, prolonged exposure to gamma rays can still cause serious injuries within your skin. So here is the heat pattern. So you have X-rays, some of the light can pass through and some of them can be blocked, and then you can easily see the projection of your bones, right? So here is the another demonstration in terms of the meter to nanometer scale. So radio waves, the wavelength is around 100 meter. For visible light is 0.01 millimeter, and then for the gamma rays is nanometer, right? So as I mentioned, the penetration power is higher here, right? So you see that the smaller wavelength, higher frequency, and then high energy hazards, right? So you have a more destruction towards the human cellular compositions. There's another demonstration you will find that the a mountain is equivalent to the amplitude modulation radio, right? So that's how big is the waves, the separation between two ends. That means the wavelength. So the wavelength is equivalent to the mountain. For FM radio, you have a football pitch, and then you have a microwave similar to the baseball. As you move along, the light bulb is similar to the bacteria, and then for the radioactive gamma material is equivalent to the atomic nuclei, so small, right? So you see that if the wavelength is big, right, you see we start from the DC where the frequency is 0. We have 3 hertz. You see we have AC power here at 50 hertz, and then you have a cathode ray tube, your monitors at around 3.5 or 3.8, and then you keep on increasing, and then for cellular communication or the satellite communication, you have gigahertz frequency, and then up to radioactive elements, you have a e-hertz, right? So it's extremely dangerous. You see, this is the spectrum that actually is responsible for the visible region. That's what we call the visible region. Before is the infrared, after is the ultraviolet. That's the only region. And remember, after this, we have some ionization, right? That means that these radiation can actually harm the cellular compositions. And before that is non-ionizing. So that's what we discussed. This is an interesting demonstration of how the EM waves are produced and generated. So you can also scan this and let me maybe play here for easy understanding. Okay, remember we discussed 3 cases. One is DC, that means static, when the charges are not moving. The capacitor is an example. Another is AC, is another is DC, when the current is flowing. The example is electromagnet, the stationary electromagnet, right? Or that acts like similar to a bar magnet. The third example is when you have a pulsating waveform, right? So this is the third example. Okay. These are the questions we will study. So I can stop every time and explain to you. So this is something related to how you can detach an electromagnetic wave from certain material, and it can travel through the medium or even in the space, right? From one end to another without using any sort of medium. Anybody who has witnessed this sort of motion in daily life, what does this up and down represents? Very simple. This is actually your AC waveform. A sine wave, B sine wave. Now, this is mathematics you see. Usually when you see the AC waveform, everybody draws AC like this, right? That's a linear motion. But in mathematics, you can also capture this into the circular motion. Remember, a vector is rotating and its projection is moving like this. So this negative and positive, you see, negative goes up and then stops, right? And then goes down, keep accelerating, and then stops. That's it, accelerating, stops, decelerating, stops, and then. So when negative goes down, positive goes up, it's like AC wave. That means you have a conductor, and then you give him a simple AC supply, an AC wave. And in communication circuit, where we get AC? Oscillator. We use oscillator. Tube circuit. We use RNC circuits. Triple pipe timer. Waveform generator. Carrier generator. These are electronic circuits that are tuned on a specific frequency. How to change the frequency? We change the resistance, capacitance, inductance, and change the frequency. That's what we do in the radio, right? So here is your AC source, right? You connect a simple oscillator here, time varying source, right? So it will, when we have a positive side at one end of the conductor is positive. So all the charges are pushed here. In the next cycle, depending upon the frequency, it will move towards the negative side and other charges are pushed towards here, right? That's the induction, right? So this is varying voltages, right? When the voltage vary, we will study in Faraday's law of electromagnetic induction. So when the voltages vary, that's the dynamics, electrodynamics. That's not DC, that's AC, right? Dynamics. So this dynamics actually produce voltages, or not produce, induce voltages in a conductor. Similar, right? So this is something, if you have heard the Norton theorem, and maximum power transfer theorem in circuit analysis. So if you want to transfer a maximum power from the source to the load, you need to make sure that the impedance, that is sum of the resistance, capacitance, inductance at the input, is equal to the load resistance. If they are matched, you can transfer the high power, full power. Otherwise, there is some loss, right? So there's a source, right? Source is antenna, the transmitter, load is the antenna, right? So you need to make sure that the impedance at this terminal is equivalent to this one. So that's how we can actually produce the EM waves, right? So this is the example of electrodynamics, right? So we move towards our next part. Any questions so far? So this was the just a fun part of our whole subject. So introduction, some, the videos, and now we are going to start our main subject. Okay, any questions so far, or you'd like to share something? Okay, good, good. Let's see. Okay. So if you look at the book notes, you will find similar material on the book page. Okay, so this is chapter number 1. Okay, so here we officially start our course. Okay, so uh, I remember in one exam I asked the what are the 4 different types of forces, right? So these are the 4 types of forces in nature. So one is the nuclear force, strongest, range is limited to subatomic level. The second one is the electromagnetic force that we are actually concerned with, and it exists between charged particles. It's dominant force in microscopic systems, right? Atoms, molecules, and its strength is on the order of 10 to the power minus 2. There are 2 more forces as well. For example, weak interaction force, it exists in the nuclear force, and another is the gravitational force that exists between the big mass particles, right? Now, we are going to study the electromagnetic force. However, we will take some inspiration from the gravity, right? So most of you have studied the gravitational force, right, in your college physics. So let's say if you have 2 particles, m1 and m2, right, uh, and the distance between them is r12, right? So you see these arrows, r12 cap. Anyone knows about this one? Why we use this one? Any idea? What does it mean? Yes, distance is this one. But why we use this bold letter and a cap on it? It's a mathematical notation. Any idea? We will review it later, don't worry. That's called the unit vector. It's called the unit vector. Unit vector. That means this will tell you the direction, right? Unit mean one, so its amplitude is one. So it has nothing to do with the force amplitude. So it only tells you the direction. So this cap means unit vector. Okay. So you see, this is moving this way. That means that the force between them is on the axis, right? So their regional axis, the point, central point. So that's the force. So this force on G12 is in this way. Force on G21 is on this way. Both will attract each other. And the formula is given by Fg21. This is constant, product of their masses, and square of the distance between them. Okay, so that's called the gravity or gravitational force. Can anybody tell me what's so special about this force? Whether this force increases or decreases, when it increases, when it decreases, what's the impact of this force from this equation? Anybody? Just an example. Yeah. Two is bigger, force is more higher, right? How about the R12, the distance between them? Smaller distance, more powerful force. How about the square? Square of the distance. Only correct. What does nonlinear mean? So this is called the inverse square law. This is called the inverse square law. So r square, 1 over r square. That means that if you are very close, so 2 square is 4, 3 square is 9, 16, right? So if you move away, it will dramatically increase the force, right? Because it's being divided. So the bottom figure or the denominator becomes non-linearly higher. So if you move a slightly away, the force decreases suddenly, right? But inversely, if you slowly come closer, the force increases dramatically. Correct? That's called the inverse square law. So why it's called inverse square law? Because it's quite common in several physical phenomena, including the electricity force, right? The electric field also follows exactly the same formula, right? Instead, rather than masses, we have charges, right? So if you have two charged particles, they will attract similar to like this. Here is the problem. You see, here we have masses. Why we put there? Because they have a very strong correlation. The formulas, they looks very similar. So in electromagnetism, we have one charge, another charge, right? So because the charge, they have field radiated from their surfaces, and they can be attracted from their line of radius. And this one charges, if the charges are more, let's say the Coulomb quantity is higher, the force is higher. However, if their distance is small, the force is very small. force is very, very high. Now, what is this 1/4 pi epsilon naught? Here we have a gravitational constant. So what is this thing? Epsilon naught. The material between charges. Remember, if the charges are in air, if you have the cotton between them, if you place sand between them, water between them, or you place some mica, glass, fiber, paper, that's it. These are all the materials that we use to create capacity. Right? That's what we call the permittivity. How the material permits the electric field to pass through it. Right? We use this property to solve many problems in the daily life. For example, in insulators, we do not want charges to interact with the pole when the conductor is passing. Right? So you have a conductor here. So we do not want charges pass through the air and come to the pole. Therefore, we use insulators. We use ceramic insulators. Right? So we have a low permittivity. So that's the formula for the electromagnetic force. We call it the Coulomb force. Okay. We will also study it later, but look at this one. We are now going to derive the concept of field, right? So we know from the previous formula that force is equal to charge 1, charge 2 over 1/4 pi epsilon naught r square, right? That's the Coulomb force. But actually now we are trying to find out how the electric field looks like. Field, we already know that any region or space where we can feel the effect of certain quantities called the field, right? Let's say if you have an electric charge, you place another charge and then it can force some force. That's field, right? You have an opposite charge, then you can feel the force. If you have a similar charge, you can still feel a field, right? So that's what we call the field. But how to represent it mathematically? We use this equation and we will derive the concept of field, right? That's very interesting. So look at the field in terms of a gravity. So we have F equals to field times mass. What does it mean? It means that when you have some mass closer to another particle, it will experience something. That's called the psi, this psi, right? But we can use this to create our own concept of electric field, right? I can again write a formula here. That's a simplified formula, right? So it means I can create something to like this. So that means that I have some test charge Q2, right? So there's a charge here and I have something, another charge. I'm bringing Q2 closer to it and it will experience something, right? Of course, there's a force, but this thing in the red region, I can consider it as a field, right? So this is a field. When I put Q2 near it, it will experience some force F, right? So you can say that this red particle now can be treated F over Q2 is equal to 1/4 pi epsilon naught r square, and that is what we can call field or E. So this is the definition of electric field. Actually, it's Coulomb law, and you can just remove one Q and put it on the other side. You can name it electric field mathematically in our rest of the subject. Is it clear? So you don't need to memorize it, right? But actually, you should know that where electric field is derived or where it comes from, right? So now you see, in electric field, we have only one charge, 4 pi epsilon at r square, and then we use this unit vector. I'll explain later where we get this unit vector. Okay. So this vector will tell us the direction of electric field. Of course, if we have charges here, our unit vector tell us that the electric field is in the direction of their radius, right? Because the other charge is directly in front of the one charge. So we have the radius direction. So capital R shows that the electric field direction is in the radial direction, right? So if you plot the field of a single charge Q, you would see that there are certain lines, you see, that are emitting or radiating from a charged particle or even a charged bulb or any sort of substance, even it's a plate. But if it is a spherical shape, you can expect the radiation of charge in the form of a spherical radiation, right? So what does these lines mean? These lines mean that if you place another charge here, it will also experience a similar pattern or similar force depending upon the nature, either it's positive or negative, right? So here we can have a concept of electric field lines, right? So of course these line will change when you have multiple charges, but for simplicity we can only consider two charges, right? If you have more than charge, two charges, three charges, four charges, then you can use vector algebra to solve the position. Some in some direction it will add, in some direction it will subtract, and then you have a resultant direction, right? So here is the principle finally represented. Let's say if you have a more charges here, you see this charge positive is going outward, negative is going inward. So this is again a convention. When we have a positive charges, right, we will use this sort of convention. When we have a negative charge, we will induce the direction of vectors inside, such as the negative will attract and positive will repel, outward and inward, right? So uh, if you have a positive direction here, negative here, then you would see that these line will add up each other, these line will add up each other, and of course these circular line again will add up each other, right? At some position they will cancel, opposite direction they will cancel, and in the same position they will add up each other. So you can again use rectangular components to derive at their positions. Okay, so we have another principle of linear superposition. That means that in a simple case, if you have two charges, we can solve them, right? But if you have multiple charges, then their effect will be added together, right? Similarly, for example, if you have two charges, we can use this formula Q1, Q2. But if you have three charges, then we can use Q1, Q2, Q1, Q3, right? And then you can take Q1, Q2, Q3 outside and then add them together. We will study this in the Coulomb's law. Okay, this is just an introduction to represent how to define electric field. Is it clear? Any question from this derivation? How to represent the electric field? So we learned from Coulomb's law that the force due to two charged particles is equal to the product divided by square of their distance, right? And the constant is 4 pi epsilon naught. Any questions? It's clear? Okay. So we have another concept of polarization. Uh, for example, if you place a positive point charge in material composed of atoms, you see, usually all the atoms uh, initially the atoms, they are randomly arranged in the structure, right? There's no position because there's no charge on the atom, right? All the atoms, finite amount of the charges, the sum of the charge on a material is zero, right? You can have a small amount of a charge but at a very small position, but when you add the whole charge on a material, the net amount of a charge is zero because they cancel out, unless you put an extra charge or you provide an energy or you put a potential or you provide a charge on it, it will have a extra charge on it. And the example is just like a comb, right? In normal condition, the comb does not attract anything, right? Because neutral, right? When you rub with the hair, due to the friction, it's charged, right? Then it can, attract something. So that's the example of of an any material, because the material, they have the atoms, they have the positive and negative polarity. So when you place a positive charge, all the atoms, they will align themselves into the direction of that charge, right? For example, you see the negative portion will be aligned toward positive, and then the positive will be into the symmetry, right? So you see all the green regions that has a negative, they are aligned according to the positive, because positive and negative attract each other. In the absence of this charge, the total E is zero. So when the atoms, they experience forces that causes them to become distorted because of this positive charge, one pole of the atom become more positive charge relative to the other pole, right? Such a polarized atom is called electrical dipole, right? We have also looked at into the video as well. And this process is called the polarization. And this effect we can demonstrate by using the E, and this charge Q can be placed here, right? So you see this formula, we can take this value from the previous slide. So this is the definition of electric field. The unit is volt per meter, but in the previous example or previous question, we have F over Q, which is Newton per coulomb, right? So both units are correct. Newton per coulomb is also correct. But in our next chapter, we will derive more formulas and we will see that the actual unit of electric field that is widely used is volt per meter, right? So uh, by looking at the volt per meter concept, what comes in your mind? Any idea? Volt per meter. Any application in daily life? As voltage is simply the potential difference, right? Volt per meter is electric field, right? Okay. Imagine this is an electrical conductor, power line. Okay. So what do you imagine? How the electric field will behave? It's good here, strong here, no? Very strong here. Right? If you move away, it decreases, right? That's the potential on this line is called voltage, and the effect of this potential at certain distance is called electric field. Volt per meter. 10 kV per meter. That's the potential difference. That's the reading we actually need to design insulators. I will show you one example in the exam question. I designed one question related to the spark plugs of a gasoline If you see this part here of a gasoline, how many of you using the bike? Or you using the bike? No. Car. Car. Who drives the car? No one is there. We will look at later. The petrol engine or gasoline engine needs spark, electric spark, right? So each piston actually needs spark. You put a fire and then do the combustion, right? That is being done through the spark plug. So the spark plug is construction is like this. So it has a coil and there's a gap. You have a strong electric field here. When you provide electric field, it produces a spark, just like a lighter. Right? That has a certain value. You know, if the spark plug is not working, you need to adjust the distance. That's you adjust the electric field. You decrease the distance, so the volt per meter is small. And then it can produce the spark. I put an exam question on this. How much voltage you need to produce this kind of electric field and tell me the distance. So volt per meter. So you have 10 kV volts divided by 1 meter is the electric field. That's it. Simple formula. So you decrease the distance and then you have a higher electric field. So it operates on a certain electric field, right? Because there's a battery and the coil behind. So that's the idea of volt per meter. So the beauty of this subject is that it will give you all the possible connections and relationship of electrical quantities. So the relationship between voltage and electric field we will study. We will derive. And the inverse relationship. So you are given voltage, how to find electric field, given electric field, how to find voltage, given charges, how to find field, given charges, how to find voltage, right? And then of course the force. If you know all this, then you can find capacitance, you can find energy. There's another important relationship that I discussed, this small e, right? Actually, we use epsilon naught for the air. That's the permittivity of the free space. That means that if the charges are placed in an vacuum or free space, there's no material inside, then the permittivity is actually 8.85. In exam paper, you will see all these the constants they are given, right? But we also use the relative permittivity. Remember, in physics or in electrical engineering, we usually baseline is free space, right? Now we have different material. Let's say I have glass, I have beaker, I have, let's say, there's a water, I have paper, right? Now, rather than calculating everyone's permittivity separately, I use relative permittivity. What does relative mean? That means that one is the topper in your class, and all the other students get relative marks. For example, the topper gets 4, other gets 3.9, 3.8, 3.7. That's a relative, right? So how much factor multiplied by the topper will get by the other? Understand? That's what we call relative. So this is free space. Permittivity of mica, glass, air, or maybe the water is equal to 0.1 times the free space. That's what we call the relative permittivity. So in experiments, in calculations, we usually give, okay, the relative permeability of this bottle is 0.1. That means 0.1 multiplied by the free space is equal to this one. Right? So then the permeability will be absolute. Similarly, we use similar concept with the materials inside the magnets. Right? So we have nickel, cobalt, iron, right? So all they are being compared with the air, μr, permittivity of the free space, permeability of the free space. Right? With respect to air, everything is compared. Right? How much iron will boost up the magnetic field with respect to the air multiplied by 5, multiplied by 6. Okay? So in this case, we use relative. You see, for vacuum, ER is 1. Of course, that is same, right? This is already vacuum. For vacuum, we use 1. If there is something more stronger than vacuum, then the value is higher than 1. If there is some student better than the topper, the factor is 1 point something. So air near the earth surface is much more better. That's something more related to the humidity side. And then let's say if you have other things other than the air, it's going to be 0.9, 0.8, 0.7. It's going to decrease the, okay? So the third thing that we usually consider in our experiment is the flux density. So the flux density is epsilon multiplied by the E, right? Because you see, E is more like a common term, volt per meter. But electric field in metallic object of copper or metallic object of iron, electric field in mica, electric field in copper is different. Understand? So in order to make it specific rather than generic, we use D, flux density. So you use material here. Put the constant of material and multiply with the electric field, you'll get the flux density, right? Because the flux density is now more like specific to the material as well. Okay, so we use D. So these are the pair, electric field, flux density, and epsilon. In our next chapters, we will also see flux density. What's the unit of flux density? Famous brand as well. Magnetic field. We have a B, magnetic field, 5, we have an H, magnetic field intensity, multiplied with the material, iron, copper, cobalt, chromium, nickel. Right, so BH is a pair and ED is a pair. Right? So these are four common definitions. Right. So these two pairs will help you to understand the electrostatistics. Right? You will derive the formulas based on these two terminologies. Okay, before we move further, maybe we take a break, right? To one, or should we continue? Okay, maybe 5-minute break and then we continue. Okay. If you do not understand, I can help.
When we went calculate, we set the zero, we set the E zero is air. Okay. Wet field is one.
No, actually, E naught is for the air. Yeah, for air is 1 point something.
So this R is
Relative.
zero.
Yeah, R, for example, this is standard, E naught is constant, right? ER is relative. That's the number. For example, you want R for beacon. For the, yes, and it's a glass or something else, then it would be, let's say, 0.9. Right? Then in here, we use 0.9 multiplied by this. Let's say if I do here, then if I multiply this, don't worry, we will solve the problem.
Okay, let's continue. So here is a small simulation for you to try. Can you please scan this code? Please scan this code, and then you will see the charges, their electric field. You will see these kind of interface, and then press this add button and you will have a positive charge here. Press negative and you will have a negative charge here. And then you can see the electric field line due to these two charges. You can also do two same charges to see that they will actually, field line will actually repel each other. Right? Now this is even more better. Now scan this and then you would see the amount of electric field, the vector. You can see the voltage. This is even more better. Please scan this code and you will experience the electric. You see, I put 1 coulomb charge here and -1 coulomb charge here. So we will have a positive to negative field lines. Now, if you place the meter or the sensor at this position, you would see that the amount of electric field is 4.98 volt per meter, right? So that means that if you have 1 coulomb charge here, 1 coulomb charge here. So you can use the previous formula, F is equal to Q1, Q2, right? And then electric field is depending on which thing? Charges are constant, right? It depends only on the distance. So if you scan this code and try to move this sensor away from positive charge or closer or even at the upper position to see how the electric field changes. So you see that the electric field would be a clear function of distance. Because it follows the 1 over r square, you will see that the electric field increases dramatically when it's closer to the charge. And when you move away, it decreases at a very sharp rate, right? So that's how you can actually simulate and learn the effect of electric field due to the presence of charges. And we will also derive the formulas that if you are given charges, how to find out the electric field, okay? Okay, let's quickly go through the magnetic field concepts, and then we try to understand the idea behind these terminologies. So previously, the magnetic interactions were known for centuries. So people uh, actually found some pieces of rocks that can actually attract metals, especially the iron, right? But actually, they do not know the reasons, or the phenomena was actually not well defined. So if a needle is placed near a magnet, it aligns along lines called magnetic field lines, right? So if you have this bar magnet and you place a needle, you would see that the direction of needle will plot these lines. Interestingly, there are certain properties of these lines. For example, they start from north and end at south into a continuous circular paths. They never break. Uh, Magnetic field, or the magnet, they has poles which exist in pairs, unlike electric charges which can be isolated. For electric charges, we can heavily charge one object or one surface or one element. So for example, if you have a comb, you can positively charge a comb, right? And it remains charged. So you don't need negative charges, still charged, right? So that means the electric charges, they can remain charged independently. They don't need negative. But for magnetic field, they always need pairs. It's not possible to have only north pole. So you take a magnet and you cut into two pieces, you'll get two magnets, north south, and you keep on breaking and you keep on getting pairs of poles. You can't isolate them. And the reason is because the magnetic field, it has to end at south pole, right? So it will create another pole, right? So these are continuous lines. Okay, that's the fundamental property behind the permanent bar magnet. Can you create your own magnet? Is it possible to create magnet? How to create another magnet? And then temporarily. Yes. And then somehow, yes, correct. That if you provide heat, and then the magnetic field will go away. Definitely, if I need a very good magnet in this classroom, what should I do? Let's say I want to make a robot. I want to pick up this platform. You follow? Yes. That's called the electromagnet. So whenever you have a conductor coil, copper coil, and then you give it a supply, DC supply, right? And then the current flow through it, right? It will create a magnetic field around the circular path of the conductor, right? So if the thumb points out the direction of a current, the curl of the finger will give you the circulation of magnetic field. So it will exist in the form of a circle, correct? And then we have a formula here. We will derive it later, but this is just to explain the concept. So the B magnetic field is actually equivalent to the current. The higher the amount of amperes you have, the stronger the magnetic field you have. And later we see that there's actually N here, right? We need terms, but we are actually simply defining the magnetic field. Therefore, I'm just looking at the conductor, not with the word terms. Okay. So I'm just talking about if you have simple coil, simple wire, then it will produce magnetic field. But if you turn this coil, right, of course, the pattern of magnetic field will be disturbed, right? It will act like a solenoid
and then the magnetic field will be like this. Okay? But in a single straight line, then the magnetic field will act like a circle, right? Anybody can explain what does it mean, R at the bottom? So R is this distance. Yeah. If this distance is very, very small, magnetic field is very strong near this conductor. If it is 1 centimeter, very strong. If it is 2 centimeter moving away, magnetic field becomes weaker, weaker, and weaker. However, it does not obey the square law we saw in electric field. Right? Electric field obeys R square. This one obeys linear R. Right? So that means that the magnetic field is strong near this radial distance, and if you move away, the magnetic field becomes more weaker and weaker. So we can only show with the one circle, but actually the field is like this. So it's spreading around that. Okay? So we have different circles, right? And then this is a conductor. You see, we will study later this phi. This phi is again a pure vector. Whenever this phi comes, that means circular direction, angular direction. Right? If I do not put phi here, nobody knows there is a magnetic field, but what's the direction? You don't know. Is this magnetic field going up, down, left, right, where? Right? So the phi tells no. Phi tells that it's going along the circulation of the conductor. That means the conductor is moving up, it's moving at this stage. Right? So we will study later on these cylindrical system. You know the cylinder, right? Everybody knows the cylinder. So the length of the cylinder is the conductor, and the angle is phi. That means the phi and length of phi is perpendicular. That's why we use coordinate system to explain these things. We use sphere, we use cylinder, and we use cube. 3 different objects to explain the field. Right? So that's the magnetic field. Similar to the epsilon naught, where we have permeability of the permittivity of the free space, we have permeability, right? That means the ability of the material to support the magnetic flux, right? For example, if you have a coil that's placed in a air, behaves different. But if you put a coil on an iron core, the flux is more stronger, right? Have you seen the motor? The winding is done on a coil with a core on it, right? Have you seen the rotor, right? There's a material, right? And then they wrap the. Why they do that? To increase this guy, right? If you use 2 amperes on wood, field is different. 2 amperes on iron, right? It's damn strong, right? That's the material. How the material supports or improves the flow of magnetic flux. So have you seen the transformers? They're heavy, not because of the copper, because of the iron. We use iron plates, right? And then we wrap the coil in iron. So the flux increases. And then you have secondary coil on it, and the flux goes smoothly towards the secondary coil, right? We will later look at that why we do insulation between plates, what's eddy current. So we need to look at another chapter to study this. Okay? So this chapter is only meant for general discussion, introduction of simple equation. Okay? So magnetic field is circular depending upon the constant being used as material and the amount of current, and is inversely proportional to the radius. So move away, decrease, right? Similarly, we use magnetic field intensity H, which is B is mu H, right? We will look at several hysteresis curves, right? So how the magnetic field and H are related to each other, right? So mu is again relative, right? Mu naught is 4 pi into 10 to the power minus 7. You will be given this uh, constant. But this is for the free space, right? For iron is different, for nickel, chromium, cobalt, they're different. Okay. So we always use mu, which is actually mu naught into mu r. So you have a relative relationship, right? So now you see we have three different characteristics. One is permittivity, how the material is good at with the flow of electric field. That's being used in capacitance cases, right? Remember, I gave you the example of power line separated with the pole. We use the insulate permeability, magnetic permeability, right? So for electric permittivity, we use farad per meter. Epsilon naught is given, and you can simplify it also. For magnetic permeability, we use Henry per meter. That is mu naught. Conductivity. What is conductivity? Flow of current. Right? So first is electric field, another is magnetic field, and third is current. So if a material is good at the conduction, right? So we use conductivity, Siemens per meter, right? So you learn conductance, Siemens. And the inverse of conductance is resistance. Or resistance is opposition to the flow of current, right? And when you check the inverse of the resistance, you get conductance, Siemens. But when you put it on a length, you have a conductivity per meter. Understand? So why we use conductivity? Because we need to make a fair comparison between the material. I ask you to give me a good material, and you have to look at the table, right? And then you say, okay, I take 1 meter gold, 1 meter copper, 1 meter iron, 1 meter another material, and then I compare the conductivity. Now it's not conductance, it's conductivity. It's used meter, right? And then you put them on a scale and you find which one is at the top. Which material should be at the top? Super. Which one? Super. Yeah, but which material? Name. Which material should have good conductivity? Gold. Gold. Gold is good. Silver, why we don't use silver? Because it reacts with oxygen. Fluid. And also, when we use silver, it heats up the terminals. Right? Therefore, in precise data transfer, just like the RAMs, processor, we use gold plating. Right? It remains, the conductance remains as it is with the passive time. Right? You see the DSLR lenses, these contacts, you need to remove many times, right? You put the lens, remove the lens, put the lens, remove the lens. So there's a slight gold plating. With the passage of years and years, they do not have to. For better conductivity, we can use silver, but it may work maybe 1 week and then we need to replace it. Copper is also good. But we use copper because it's soft. We can turn, do the wiring, sealing, and seed wiring. So different properties we use at different applications. Silver is good. You see the power lines, we use silver, right? Okay, maybe we finish it here. And yeah, and then I will continue next. So for today's lecture, not as one thing, very important to look at that. So in our next lecture, today it's more like talking about the table. In the next lecture, then I will, give you some topic to solve. Whenever there is a question that looks like the sample perspective there, I'll highlight it, right? So then there is something that you need to get when you solve it. So when we are talking, definitely we are discussing something. We want to understand. When it comes to the solution, very quick. When it comes to the solution, it's very, very quick. But the problem is, you need 2 hours of understanding to solve 5 minute question. The solution is very simple, but you need to understand it. And in order to understand, we need to our lecture. Okay, so I will spend more time to explain the things. When it's clear, everything is clear, basics is clear, mathematics is clear, then you will start solving the question. And every question, I'll give you the hint that this is the nature of question I will ask in part A. This question I asked in part B. Then you have to do it. Thank you.